All right, so hopefully if you struggled with the first handout for this section, hopefully the second handout went a little more easily. I don't think that it's any more difficult. It is slightly different, of course. It's not any more difficult, so hopefully the first handout made things easier. So we have a vector field that is two-dimensional, so I'm only graphing it along a line, but the horizontal coordinate is always 0, and the vertical coordinate is going to vary as we move along the x-axis here. So we're trying to think about whether this vector field looks like it's circulating around the point A, and we're always measuring the direction of circulation with the usual angle convention, which is that counterclockwise is going to count as positive and clockwise is going to count as negative, right? That's the normal angle convention. So for this first example, if a fluid is flowing down to the left and up to the right, you can imagine like a little paddle wheel sitting in the plane and just thinking about which direction is the paddle wheel going to want to move. Well, if the right side is being pushed up and the left side is being pushed down, it's going to want to move this way, that is clockwise. And so this vector field, it looks like it's circulating positively around the point A. Okay, for B, well, this example is also pretty clear. If the right side is flowing down and the left side is flowing up, this is circulating this direction, clockwise, around the point A, and so that's a negative circulation. All right, for part C, this one isn't as obvious because on both sides of the point A, the vector field is flowing up, but the vector field on the right is flowing up much more than the vector field on the left. So if we had a little paddle wheel, right, with two arms sticking out to either side of A, the vector field pushing on the right side is pushing a lot harder than the vector field pushing on the left side. And so the right side will win and the paddle wheel will turn this way, counterclockwise, and so that's a positive circulation. And then for part D, the point is over here. So for part D, it's similar to part C, but in the other direction. This time the vector field to the left of A is pushing harder upwards than the vector field to the right of A. And so this is going to circulate clockwise, and that's a negative circulation. Okay, now for each of these, estimate whether this function is, our coordinate function is increasing or decreasing. So as we move in the x direction, for this first example, to the left of A, n is clearly negative because these vectors are pointing down. To the right of A, n is positive because these vectors are pointing up. And so that means, right, as we move rightwards, n is going from negative to positive. So that means, in example A, n is increasing. And that means that the derivative of n with respect to x is positive. And notice that this is with respect to x because we're moving in the x direction as we do this. Okay, for example B, right now n starts out positive, and as we move rightwards, n becomes negative because these vectors are pointing down. So for part B, n is decreasing, and so partial n partial x is negative. For part, I don't know if you can hear the people with the chainsaws outside. For part C, n is positive, but it starts out small, and as we move rightwards, it gets bigger. So it's going from small to big, and so for C, when n goes from small to big, that means it's increasing, and so this derivative is positive still. And for part D, it's n is starting out big and becoming small. And so for part D, n is decreasing, and so partial n partial x is negative. Okay. Now for number 3, what I hope you noticed is that whenever this derivative is positive, we have a positive circulation. Right? When this partial derivative is positive, we have a positive circulation. When this partial derivative is negative, we have a negative circulation. And that doesn't seem like a coincidence, right? So what it seems like is that when partial n partial x is positive, we have a positive circulation. and when partial n partial x is negative, seems like we have a negative circulation. Okay. All right, so let's see if this works with a worked example. So first let's calculate this circulation derivative, partial n partial x, for this particular example. So the partial derivative of cosine x with respect to x is minus sine x. Okay, so let's see what this is doing at these three x values. So at x equals minus pi over 2, right, minus sine of minus pi over 2 is plus 1, right? We get a minus minus 1, so that's plus 1. So this leads us to believe that at x equals minus pi over 2, this vector field should be circulating positively. And remember, that's counterclockwise. Okay, so now let's check what's happening at 0. When we plug 0 into this, we get 0. And so here we think there should be no circulation. And then at x equals plus pi over 2, then we get, right, minus sine of pi over 2. That's minus 1. And so we should get a negative circulation, that is clockwise circulation, at pi over 2. So to see if this turns out right, let's again plot our vector field to see what we get. So cosine of cosine of 0 is 1, so that's going to look like this. And then this point here is pi over 6, so cosine pi over 6 is root 3 over 2, like this. Cosine of pi over 3 is a half, so like this. Cosine of pi over 2 is 0. And then I guess this point here is going to be 2 pi over 3, or 4 pi over 6, right? Each step here has size pi over 6. And cosine of 2 pi over 3 is minus a half, so like this. Now moving into our negative x values, here at minus pi over 6, cosine is root 3 over 2. At minus pi over 3, it's a half. At minus pi over 2, cosine is 0. And then at minus 2 pi over 3, cosine is minus a half, so like this. All right. And now comparing the graph to the results of our calculation, at minus pi over 2, it looks like, right, the vector field is up to the right and down to the left, so this is definitely circulating counterclockwise, which matches what we found. At x equals 0, right, this vector field is sort of pushing equally hard on both sides and up on both sides. And so these two are sort of balanced, it seems like, and so that would be no circulation. And then at pi over 2, with the vector field flowing down to the right and up to the left, that's definitely going to be causing a clockwise circulation, which matches what we found here. So, the point of this whole exercise for this example is just to build our confidence that partial n partial x really measures what we want it to measure. It measures circulation. Right? So if we want to know, at least for a one-dimensional vector field like this, if we want to know about circulation, we can look at partial n partial x. All right. So yes, everything matches. All right, for these vector fields, well, now we have to think a little harder because these are two-dimensional vector fields, right? And much like with our divergence example, we know at least in the x direction what to look at to measure circulation, look at partial n partial x, but we should think about in the y direction what kind of change would cause a positive circulation. So for this particular graph, for this particular vector field, at the origin, it definitely looks like it's circulating in the positive direction because, right, everything is circulating around the origin here. So we think that this should probably have positive circulation. But partial n partial x, that is only picking up the positive circulation caused by the vectors to the left being down and the vectors to the right being up. So let's think about what happens in the vertical direction. Well, in the vertical direction, the vectors above are pointing left and the vectors below are pointing to the right. Yeah? And so even if we didn't know about the vectors to the left and right, if we knew about the vectors above and below, it still looks like this would be causing a positive circulation. So there's another contribution to circulation that isn't caused by this partial derivative with respect to x. Right? This is a change as we move in the y direction, so this is some partial with respect to y. But what's changing? Well, it's the x-coordinate of the vector field that's changing, and it's decreasing, right? So we need to see what's happening to the x-coordinate, right? We need a derivative of our x-coordinate function, but a positive circulation is when this is negative. So we need a minus sign here and not a plus, right? Because now when this one is minus, this minus sign will make it a plus, and that is causing a positive circulation, right? So we have to be careful with this minus sign right here. So now we think we have an expression that accounts for both directions, the x direction and the y direction, and that measures circulation. So let's actually calculate for this example. So partial n partial x, so the derivative of x with respect to x, that's 1, minus, and then calculate the derivative of minus y with respect to y, and that's minus 1. So 1 minus minus 1, that's 2. And so this vector field appears to be circulating in the positive direction everywhere. Right? In principle, this circulation expression gives us a function of x and y, but for this particular example, it turns out it's constant. We definitely believe that the circulation is positive at the origin, but even if we look away from the origin, right, vectors out in this direction are pointing that way, but they're longer than the vector down here that's pointing down and to the right. The vectors here and here are pointing towards or away from the point, and that doesn't cause any circulation. I've made a mistake here. This is pointing the wrong direction. So the vector above and to the right is longer. The vector below and to the left is still pointing this direction, but it's shorter than the one up and to the right. So the one above and to the right wins and causes this clockwise circulation. So, right. So we can talk ourselves into believing that the circulation around this point is indeed positive. And we could do the same kind of persuading of ourselves for points in every quadrant, right? So it is plausible that circulation for this vector field is positive everywhere, and that is what we find when we compute this quantity. All right, let's look at this vector field. Before we do the calculation, let's actually estimate. So let's say right here. So the vector above is pointing right. The vectors below are pointing also to the right. It's a little hard to tell, but if you zoom in on the PDF, that is what's happening. But the vector above is much longer than the vector below. So just looking at the vectors above and below, it looks like the circulation is going to be clockwise. If we look at the vectors to the right and to the left, well, they're both pointing to the right through this point, right? And vectors that point through the point, they don't really contribute any rotation. So those don't affect the circulation. And so it looks like we're going to find a negative circulation, at least at this one point. So with that in mind, let's actually calculate the circulation. So partial n partial x minus partial m partial y. So n is 0, so this first part is 0, minus partial m partial y, derivative of e to the y with respect to y, that's e to the y. So we get minus e to the y. So what we found, right, this e to the y is always positive, and so minus e to the y is always negative. So this vector field appears to be circulating in the negative direction everywhere, which, is true because for every point, the vector immediately above it is bigger than the vector immediately below it. So we always get this negative circulation. But what this is telling us is that it's not just the case that this vector field has negative circulation everywhere. It's also telling us that as you go up the y-axis, the circulation gets bigger, right? Because when y gets bigger, negative e to the y, it gets more negative, and so we get more negative circulation the further up the y-axis we go. All right, so let's look at one more example. Sine y comma cosine y. You can see that there are some places around here where we clearly have positive circulation, like right here, and some places where we clearly have negative circulation, like right here. Okay, so let's calculate our circulation. So partial n partial x minus partial m partial y. So we're going to get, let's see, this, sorry, the derivative of cosine with respect to x, so that's minus sine x minus, and then derivative of sine y, that's cosine y. Okay, and then we could just check a couple points to see that this formula really is telling us with the formula what we can see on the graph. So this spot here where I put the plus, that looks like it's probably minus pi over 2 comma pi. Sorry, yes, comma pi. So if we evaluate this at minus pi over 2 comma pi, what we get is, let's see, minus sine of pi minus, that's not right, minus sine of pi over minus sine of minus pi over 2, there we go, I got there eventually, times cosine of our y-coordinate, which is pi. Okay, so minus sine of minus pi over 2 is minus 1, minus cosine of pi, cosine of pi is minus 1, so this whole thing is plus 2. So that verifies what we can see on the graph, that the circulation around this point is positive circulation, counterclockwise circulation. And I left the last page blank for some reason.